Well, hello again, ap2. Let's start up chapter 9, video part 3. We're going to be talking about Pascal's principle. Pascal's principle will be starting in your textbook on page, I think, 279. All right, Pascal's principle. Pascal's principle states that a change in pressure applied to an enclosed fluid is transmitted undiminished to every point of the fluid and to the walls of the container. I'll say it again. Pascal's principle states a change in pressure applied to an enclosed fluid is transmitted undiminished to every point of the fluid and the walls of the container. So what this means is if you take an enclosed fluid, say a balloon full of air, and you squeeze one side of the balloon, you grab it with your hand and just squeeze your fingers down, the pressure in the balloon will remain the same everywhere. The pressure in the balloon is going to increase because you're squeezing on it, but it'll increase everywhere. You're not going to have one side of the balloon at high pressure and one side of the balloon at low pressure. It distributes undiminished everywhere, okay? Well, what does that do for us here? Well, this gives us rise to something called hydraulics. The brakes on your car, for example. How do they work? You must have noticed that when you're driving, you press the brakes on your car with a fairly light amount of force, and that entirely massive, going incredibly fast car comes to a screeching halt. It must have occurred to you at some point that the amount of force you're applying to your brakes is not nearly enough to actually bring that car to a stop. Something else must be going on. You must be getting some sort of mechanical advantage. That mechanical advantage is resulting from Pascal's principle and the use of Pascal's principle in the design of hydraulics. Let me give you a diagram here and show you what I mean. Hydraulic systems are basically going to be a pair of movable pistons connected by some hose, and that hose is filled with some sort of fluid. So, for example, let's try drawing this. Wish me luck. I could have a cylinder connected to another cylinder with a hose. And in that cylinder, I'm going to have a movable piston. So there's a movable piston, and here's another movable piston. Okay? So we're going to say that I can apply forces on this piston, and it will move. If I apply a downward force on this piston, the piston will move this way. If I move this piston this way, the fluid inside, we're going to say, is uncompressible. So if I move the piston this way, that's going to push fluid such that this piston is going to go upwards. So if I apply a force here, there will be some other force applied by that piston that way, right? If I push down on this piston's going to go up. Now, what does this do? Well, let's think about this for a second. If I move that piston, some displacement, and this piston is going to move some other displacement. This piston is having cross-sectional area 1, and this piston is clearly bigger. It will have cross-sectional area 2. Okay? Let's move myself up a little bit, give myself a bit of room. Pascal's principle is saying that the pressure over here has to be the same as the pressure over here. Okay? So, what does that mean? Well, pressure is force per area, and that has to equal the same force per area. Now, the areas are not the same. You will have noticed that Area 2 is bigger than Area 1. Area 2 is much bigger than Area 1. So, if we do a little bit of algebra, you can see that F2 is going to equal to A2 over A1 times F1. A2 is bigger, so this ratio right here is greater than 1. So force 2 is equal to a number bigger than 1 times force 1. In other words, F2 will be greater than F1. I have achieved some amount of mechanical advantage. The force at the big piston is going to be bigger than the force at the little piston. How does this apply to your brakes? Well, crudely speaking, your brakes at the other end, at your pedal inside the car, there is going to be a small piston, and that piston is going to push against some hydraulic fluid, basically brake oil. And you're going to push on a little piston, and you're going to move that brake a big distance. At the wheel, inside the brake caliper where your brake pads are, there's going to be a much larger piston. That larger piston is going to move a small distance, but with a much, much larger force. The scaling factor for that force is just going to depend on the difference of the two areas. Another point I want to make right now is with terms of volume here. The volume of fluid moved here, if the fluid is not compressible, has to be the same as the volume of fluid moved here. If I move 1 liter of fluid, 1 liter of fluid will move over here. What does that mean? Well, another way to look at that is you've got a little area and a big displacement has to be equal to a big area and a little displacement. Why? Because area times displacement, area times length, that's volume. And that has to be the same as the volume over here. The fluid's incompressible. So that's why you're going to have a big displacement on one side and a little displacement on the other side. All right. Let's see if there's anything else I should say about that before we continue. Nope, I think that about covers it. I'll do a demonstration, and we'll do a example problem in class to cover this concept a bit more, but there you have it, hydraulics and Pascal's principle. Let's go on to the next topic. The next topic is going to be the concept of what floats your boat. What floats your boat? You must have at some point wondered how it is that I could take a chunk of metal, throw it in the ocean, and it's going to sink. We all know that. However, isn't it strange that I could take that chunk of metal, build a boat out of it, and not only would that boat float, I could fill that boat full of a whole bunch of other chunks of metal, and the whole thing floats. We call those tankers or transport ships. How weird. Metal sinks, but I could build a boat out of it that would not only float, but could be used to haul more metal. How amazing. In other words, if I take that metal and create it like this, and make that metal this shape, that's my crude cross-section of a boat, this one floats, the other one sinks. So what we want to do now is explore this. The reason behind this phenomenon is Archimedes' principle. Archimedes is the guy that was taking a bath and jumped up screaming Eureka and went running around town naked, all excited. Archimedes' principle states that any object completely or partially submerged in a fluid, remember fluid could be liquid or gas, completely or partially submerged in a fluid is buoyed up by a force with magnitude equal to the weight of the displaced fluid. So, let me say that again. Archimedes' principle states that any object completely or partially submerged in a fluid is buoyed up by a force with magnitude equal to the weight of the fluid displaced. So what Archimedes' principle is saying is, if I take some chunk, steel say, and I submerge it underwater, the water is going to exert some force that way. And we're going to call that the buoyant force. The water is going to the fluid will exert some force upwards, and that is called the buoyant force. The only other force at play here that we'd be interested in would be the gravitational force, just to remind you. Now, let's see this. Archimedes says that the force that's being pushed upward is going to be equal to the weight of the displaced fluid. Well, here's a way to think about that. If I put that piece of steel in the water, then that piece of steel is now occupying a space that used to be occupied by water. That steel had to move that water out of the way so it could occupy the space. Well, the force required to move that water out of the way is just going to be equal to the weight of that water. Well, the water is going to respond with a Newton's third law reaction force. So the water will exert that same force back on the piece of steel. So the force the fluid exerts is going to be equal to the weight that you have displaced. The weight of the displaced fluid gives you the buoyant force. The next concept, why is the buoyant force upwards? Why does the water exert a force upwards? Well, this goes back to the previous class discussion where we talked about the fact that the deeper you go in a fluid, the greater the pressure. And if you remember, if we submerge into a fluid, we'd get a force here and a force here, and the forces at all other locations around the surface net canceled out. However, because the pressure down here is greater than the pressure up here because we're at a greater depth, force 2 has to be a bigger force, right? Force 2 per area is bigger than force 1 per area. So necessarily, force 2 is greater than force 1. Well, the buoyant force is being described as just the difference between those two forces. The fluid is exerting both of those forces. Those combine to be the buoyant force. The buoyant force is just going to be the difference between those two forces. Force 2 is greater than force 1, so B is going to be up or positive. So our buoyant force is upwards. All right, hopefully that's so far so good. Let's see, going back to floating and sinking. If the buoyant force is smaller than the gravitational force, in other words, gravity's pulling large, buoyant force pushing small, the object will sink. If the buoyant force is greater than the gravitational force or then the object will rise. If the buoyant force is equal to the gravitational force, the object will float. It'll stay stationary, no net force. So whether or not something floats or sinks is going to depend on the buoyant force. The buoyant force is just going to be a force equal to the weight of the displaced fluid. So let's go back here. If I look, and I didn't do a good job of drawing this, so let me try drawing this again. There's my piece of steel, and now I'm going to make a big boat out of the piece of steel, but this is going to be really thin, so the volumes are the same. Okay, so assuming that that volume is the same as the volume of steel there, then what do we get? Well, look here. This piece of steel is displacing that amount of fluid. The weight of that fluid is smaller than the weight of steel, so down it goes. If I stretch that steel out into this enormous shape, look at how this volume of fluid I'm displacing. I'm displacing a huge amount of fluid now. The weight of all of that water is actually greater than the weight of this piece of steel. So the water's exerting a bigger force. The boat floats. Kind of neat. So that is what floats your boat. All right. What is a mathematical term for the buoyant force? Well, Archimedes said that the buoyant force is equal to the weight of the displaced fluid. The weight of the displaced fluid is mg, and to remind you, we mean displaced fluid. We are not talking about the weight of the material itself. We are talking about the weight of fluid displaced by the material. Okay? Well, what is the mass of the displaced fluid? Well, the mass is going to be the density of that fluid times the displaced volume. So the buoyant force is going to be the mass times g. And to remind you, this is all in terms of the displaced fluid. That is the density of the fluid. That has to be the volume of the fluid, and g, well, we know what g is. Okay? Now, the displaced volume. The displaced volume. Here's some water. If I have an object like this, all the way submerged to a fully submerged object, the fluid's volume, the volume of displaced fluid in this case, would happen to be the same as the volume of the object itself. They're both the same volume. The object is fully submerged. If, however, we have an object like this that's floating on the surface, the displaced fluid is only this volume. which is not the same as the volume of the object itself. Remember, it is critical. That volume right here, the displaced volume, is the volume displaced by the object, which is not necessarily the same as the volume of the object. And when we start doing a practice problem or two, this will all become more and more clear, I hope. So as far as I can tell, that's all I should say about this. I'm going to let it go here, and we'll talk to you live.